here we go. Okay, so the rate of change is equal to the slope. What expression would you write down for the rise? What is delta x here in terms of symbols that we have on the board already? And what's delta t in terms of symbols we have on the board?
Well, I guess x would be, no, I mean the rise would be x t plus h over minus x plus t.
Yeah, because the rise is this, well, it's also here because these are right angles. And this is at a right angle with this, which is at a right angle with this, which is at a right angle with this. Okay? So you can use a simple geometric argument to show that that distance has to be the same, but what's the displacement from here to here? This is the displacement on the x-axis from x of t to x of t plus h, right?
Mm-hmm.
Okay? Now, what's the displacement from one point on an axis to another? How do you get the displacement? We did that the first day, right? What did you do to get the displacement?
You went rate of,
What's the displacement from x equals a to x equals b?
well, it's like the distance between them, and it can be positive or negative.
Okay, but there's one single calculation you can do that doesn't, so that you don't have to worry about whether it's positive or negative.
It's the original, no, it's the final number subtracted by the original.
Final number minus the original
There
number,
you go.
right?
Yeah.
Okay. Remember that from 3 days ago or 4 days ago? Okay. You know, those first sequence of problems, if you look at them again, and it'd probably be good if you would, that first sequence of problems establishes that to get the displacement from one point to another, you subtract the first point from the second, right? So that displacement is x of t plus h minus x of t. Okay? So go back and look at how the first 12 problems, which were pretty straightforward, established what we do to get a displacement, okay? Because that's really kind of critical. I mean, for just a whole lot of things you do with mathematics, okay? Well, the displacement here, what's the displacement here? Well, it's this minus this, right?
Yeah, the final number minus the original number.
Now I'm just going to put dots. It's a displacement from t to t plus h, right? We don't have room to write out all the words, but it's t plus h minus t. And what's that equal? T plus h minus t.
H.
Simplified algebraically, you can remove those parentheses. You can move this t over here but by the associative law, right?
Yep.
And, well, some other stuff. But you know that you can do that. T minus t is 0. So t plus h minus t, well, I can say that's equal to t minus t plus h, which is 0 plus h, which is h. Just to write it out in detail. Okay? Okay, so what's the slope? Better write it like this. Well, you know what that is? There's a different name for it. Anybody want to identify the name? Seen that before?
Oh, what? Is that one the earlier?
Good. Difference quotient.
Yeah.
It's the name of it, right?
Yeah.
Y'all familiar with the name of it? You know, it's just different thing, how they simplify it and stuff. Okay? Well, that's the difference quotient, and this is why it's important. Gives you the instantaneous rate of change. Okay? If you let, in this case, instead of epsilon, you've got h, you ask yourself what happens as h approaches 0, right? Okay, so we're going to do a little more with that. We'll actually simplify one. But this is what it is, and this is your first example of why it's really important.